Welcome to this course on stochastic modeling. In this lecture we will discuss about the continuous time Markov chains. Before we get into the formalism of continuous time Markov chains, we have to review two key ingredients for developing the formalism of continuous time Markov chains. They are the exponential distribution and the Poisson stochastic process. We will henceforth abbreviate the continuous time Markov chain and refer to it as CTMC. First we will discuss the exponential distribution, state it, and define some of the useful properties of exponential distribution, and then we will move on to the Poisson stochastic process. Then we will see how these two fundamental principles can be used to construct the formalism of CTMC. So, a continuous valued random variable is said to have an exponential distribution, or its probability density function is said to be exponentially distributed with a parameter lambda. So it has one parameter only that completely defines the distribution. This parameter has to be a non-negative number. So lambda has to be greater than or equal to 0. Well, what is the characteristics of the exponential distribution? The probability density function PDF has to take a particular form. If x is the random variable, its probability density function denoted as small f of capital X of small x. Capital X denotes the random variable, small x denotes the value taken by the random variable. So it should be of the form lambda into e power of minus lambda x whenever x is greater than or equal to 0, and 0 for x less than 0. So the whole negative axis, x-axis, the density function is 0, whereas on the positive side of the x-axis, it has a decaying nature and it decays exponentially. That is why we refer it to be an exponentially distributed random variable. So first you recall that by density function what we mean by it is the probability that the random variable takes value between an interval x and x plus dx is given by the product of the density function evaluated at x multiplied by the interval size dx. So probability that x lies between small x and x plus dx is fx of x into dx. Okay, so now we will look at a figure that shows the way the exponential distribution can be plotted for three different values of the parameters. We will take three values, lambda 1, lambda 2, lambda 3, and plot the exponential distribution. Figure 7 shows an exponential distribution, but it is a very rough sketch. X is a continuous valued random variable and the density function is also continuous one, but here we have just shown a piecewise linear representation of it for the sake of illustration. So here lambda 1 is greater than lambda 2, and in turn lambda 2 is greater than lambda 3. So three values lambda 1, lambda 2, lambda 3 are used to plot this one. If you look at the curve, first as given here, on the negative side it is completely 0, that is why it is not being plotted. For x greater than 0, it has an exponentially decaying one. At x equal to 0, you will see that e power of minus lambda into 0 is 1. So its value is lambda. So it starts at a value lambda at x equal to 0. So for three curves with parameters lambda 1, lambda 2, lambda 3, they all start at a value of lambda 1, lambda 2, lambda 3. Because lambda 1 is greater than lambda 2, in turn lambda 2 is greater than lambda 3. The curve for the lambda 1 starts at a higher value than lambda 2 and so on. That is the first this one. Then they start decay. Again, the rate at which they decay is proportional to the parameter. So lambda 1 being greater than lambda 2, lambda 1 decays much faster than the curve corresponding to lambda 2. So you would see that it decays faster, which means that it will cross over the curve corresponding to lambda 2, and after a particular value, the curve corresponding to lambda 1 will be below the curve corresponding to lambda 2, and the curve corresponding to lambda 3 will be above lambda 2 and so on. So this is how it shows up. Again, another way of understanding why this crossover takes, they may not cross over at the same point. Okay. Another way of understanding why it happens is, we know that the total area under the PDF has to be equal to 1. So if it starts at a higher value, so as we progress, more area is covered by the curve corresponding to lambda 1. To compensate for that, it should be lower than the curve corresponding to lambda 2 and in turn lambda 3 and so on. Now coming to the representation, because the exponential distribution is quite often used, we say that x is a random variable which is exponentially distributed with a parameter lambda using a shorthand notation. X is, this is the symbol tilde or similar to, okay, that is, it is exponentially distributed with a parameter lambda. So exp indicates that x is a random variable, it has an exponential distribution, and the only parameter that defines the exponential distribution, lambda, is being given here. So whenever we encounter this kind of a notation, we understand that x is exponentially distributed with parameter lambda. Now we will look at the cumulative distribution function CDF of an exponentially distributed random variable. It is denoted as capital Fx of x, and by definition it is the probability that the random variable is less than or equal to the given value small x. It can be obtained from the probability density function by integrating from -infinity to the value x, like this. That is integral -infinity to small x fx of x dx. So if you do an integration of this one, starting from -infinity, when you integrate up to 0, the integral will be 0, because there is density function do not contribute till 0. It is flat till 0 and takes a value 0. So obviously CDF also is 0 for x less than 0. After beyond 0, the curve starts contributing, PDF starts contributing, and if you integrate, you would get the value 1 minus e power of minus lambda x. Okay. So again, there is a way of you can plot it in the same curve that we use for the density function. So if you look at how it the CDF will look like, for x equal to 0, e power of minus lambda 0 is 1. So 1 minus 1, it is 0. CDF starts at 0 at x equal to 0. And as x increases, this factor decreases, and therefore it will be an increasing function. In particular, it will be a monotonic non-decreasing function, because strictly increasing function, because as x increases, this factor keeps decreasing, and therefore 1 minus this factor will keep increasing. When x equal to plus infinity, e power of minus infinity is 0, then fx of x equal to 1. So it will start from 0 at x equal to 0 here, and it will slowly increase and reach 1 wherever the 1 is there here. So it will start increasing and it will asymptotically approach 1. Different CDFs will have this kind of a nature, and so on. When lambda is more, you will see that this decay will be more, and therefore it will quickly settle to 1 faster for a larger lambda. We can also come up with the complementary cumulative distribution function, abbreviated as CCDF, which is nothing but 1 minus the CDF, that is 1 minus fx of x. So obviously 1 minus fx of x is nothing but e power of minus lambda x for x greater than or equal to 0, and you will see that so this is how it is. And okay, for x greater than or equal to 0, it is e power of minus lambda x, and of course this has to be 1. So we will make use of this CCDF often in our in solving problems, and it comes handy in interpreting the way the function evolves and solving many problems. First we will look at the mean or the expected value of the exponential random variable x, indicated as e of x, and by definition it is integral of the density function with a weightage factor of x, that is integral minus infinity to plus infinity x into fx of x dx. For the case of the exponentially distributed random variable, if you substitute in place of fx of x lambda e power of minus lambda x, and you can, this is valid only for x greater than 0. Till 0 it is 0, so that will not contribute anything. That is integral minus infinity to 0, that part of the integral is 0. So integral 0 to infinity x lambda e power of minus lambda x 0, lambda x dx is what you have to do. You can take lambda outside and do the remaining integration. You can do it by parts, integration by parts. That will lead to 1 over lambda. So what you can do is you can use the formula integral u dv equals to uv between the two limits 0 and infinity minus integral v du. Take x as u and e power of minus lambda x by minus lambda as dv, and so on. Then in this way you can proceed and you can get 1 over lambda as the average value. So what we figure out is that lambda is called as the parameter of the exponential distribution, and we will also call it as the rate, because it is the rate at which the exponential distribution decays, and the average value is given by, the expected value is given by 1 over lambda. So if the parameter lambda is more, the expected value is less. So you can see here from this curve, lambda 1, lambda 2, lambda 3, you will see lambda 1 is greater, it is expectation value will be much lesser. You have to just look at when its expectation will come. This is x, and which will be a linear curve like this, 45 degree. multiply it by this density function and then integrate it out. Okay, so you will see that the expectation for this one will be lesser, lambda 2 it will be more, and so on. You can go ahead and then find the second moment also, and then the variance, that is expectation of x squared can be found out by again putting x squared into fx of x dx and do the integration by parts twice and get the value of the second moment. And then you know variance of x is expectation of x squared minus expectation x the whole squared. That way you can find out. But we will use a rather elegant approach, easier approach, that first we will find out the moment generating function for the exponential distribution. Using that we will find the second moment and then the variance. So by definition the moment generating function MGF of any random variable, continuous valued random variable, is given by g of t is equal to expectation of e power of tx. So if x, capital X, is the random variable, you take the function e power of tx, where t is an auxiliary variable, and find the expectation. That would be a function of t alone. So that is what we call as the moment generating function. So let us evaluate it for the exponential distribution. So expectation of, you define a function g of x, which is e power of t into x. So this is nothing but taking the expectation of the function g of x. What is g of x? Is e power of tx. Again, expectation of g of x is nothing but, by the law of unconscious statistician, it is integral minus infinity to plus infinity g of x fx of x dx. Putting g of x is equal to e power of tx, we get the MGF, that is e of g of x, or e of e power of tx, as integral minus infinity to plus infinity e power of tx fx of x dx. In place of fx of x, you put the density function of the exponential distribution, which is lambda e power of minus lambda x into dx. So you can take lambda outside. You will get that, take the exponential and the common exponent together, that is e power of t minus lambda into x dx. We have already seen, okay, with regard to the, while deriving the mean, that if you have an integral of this form, you will see that it is nothing but 1 over t minus lambda into e power of minus t minus lambda x between the limit 0 and infinity. Okay. So you will see that into x. If you will see that, that will become actually 1. So you will simply have that vector of lambda minus t. That is, if we have an integral of this form, it will give you 1 over lambda. This is how we got the mean of the exponential distribution. So now we have got t minus lambda, and we can write it as minus of lambda minus t, and therefore we will have, this will be 1 over lambda minus t, multiplied by this lambda, will get lambda by lambda minus t, and that is the MGF, g of t. Now how do we get the second moment from the MGF? We use this formula that you have to differentiate MGF twice and substitute t is equal to 0. So tau squared g of t by tau t squared. Of course, this is only one function of t alone. We can use the ordinary differentiation, not necessarily the partial one, and substitute t is equal to 0. So if you would see that one time, we will see that it is lambda by lambda minus t into lambda minus t to the power of minus 1 with a minus all these will come. You will see that you can proceed like this one, and finally you will get it will be equal to 2 by lambda squared. So this is the second moment. Variance can be obtained by subtracting from the second moment the square of the first moment. We already saw the first moment is equal to 1 over lambda. So it is 2 by lambda squared minus 1 by lambda the whole square, which will simply give you 1 over lambda squared. So variance is 1 over lambda squared, and the standard deviation, which is the root of variance, is 1 by lambda. So we have here a case where the expectation is also 1 over lambda, the standard deviation is also 1 over lambda. It's very peculiar to exponential distribution. Then we will get into a very interesting property of the exponential distribution, which we will make use of in developing the CTMC formalism. Actually, for a continuous time stochastic process to have to be a Markov process, then you will see that the time it resides in any given state has to be exponentially distributed. Then only the memoryless property will lead the process to be a continuous time Markov chain. See, in the case of Markov chain, we saw that the probability that the process goes from a given state to another state depends only upon the state in which it is present, and not on how it came to that state. That is okay for a DTMC because state transition occurs at particular regular time intervals. But in the case of CTMC, we observe the process continuously, and therefore at any given time the state transition can occur. So we not only look at when we talk about the probability that the process makes a transition from state I to state J, if it is in state I, it is just not enough that the state from which it entered I should not matter for finding the probability that it makes a transition from I to J. It is actually, we will talk about the rate at which it makes a transition from I to J. Further, how long it has been in I should not also affect the probability of the transition rate. So the time at which it has been residing in the state I should also not affect the probability, the rate at which it makes transition to different states from I. For that, the memoryless property is crucial. Okay. So what it signifies is as follows. Before getting into that, we will take a simple example. Suppose you go to a new town and then you are interested in taking a bus in that town. So you wait in a bus stop, and because you are totally new, you ask a local person how frequently the bus is. The person tells that bus comes very randomly, but on the average you will have one bus in every 3 minutes. That's all you can tell. You can't tell anything beyond that. So you think that it can be modeled as an exponential distribution. Okay. Okay, now let us say the mean of 5 minutes, let us say, which means that it is exponentially distributed with the mean of 5 minutes. So you stand in the bus stop with an expectation that in roughly about 5 minutes a bus will come. It may come before that or it may come later, but that is the expected waiting time for that. Then suppose you have been waiting and 3 minutes has passed. Now you again ask a question, how long we have to wait more? If you look at the remaining time you have to wait to get a bus, that again it's a random variable. Okay, the original time you have to wait starting from the time you arrived at the bus stop is a random variable. which you have already modeled as an exponential random variable with a parameter lambda equal to 1 by 5. Now you have waited for 3 minutes. It hasn't arrived. The remaining time you have to wait is again a random variable. How will that be? Will it be exponential or different? And what will it be its mean? Will it be 2 minutes or it can be more than that? Because the arrival of bus is totally random, the fact that you have waited for 3 minutes is not going to affect the arrival of the next bus. Okay, they are independent process, independent. The causes behind the arrival of buses is totally will not in any way be affected by you being waiting in the bus stand for 3 minutes. So you can tell that again you have to wait in a bus stand whose average will be 5 minutes. Okay. So of course this may be little idealistic in a real time scenario, but this is how the exponential distribution is characterized by. So the remaining time is again exponentially distributed with the same parameter lambda. So we will now formalize this idea. Let x denote the random variable which is exponential. Then you observe the random variable. Or we will say x is a random variable which is the time you have to wait for an arrival of an event. And you are observing the occurrence of the event, it has not occurred. And yes, time has passed, which means that the random variable has to be greater than s, conditioned by the fact that the event has not occurred till s. Now you ask the question, what is the probability that x has to be greater than s plus t given that x is greater than s? Okay. Well, now how do we evaluate it? This is probability of a given b, that is probability of a intersection b, probability of b. So on the numerator you will have probability of x greater than s plus t, comma x greater than s divided by probability of x greater than s. If you look at these two conditions, you will see that the first condition implies the second. So you can drop the second one. You can simply write it as probability x greater than s plus t divided by probability x greater than s. So x being an exponential distribution, what we are asking above is nothing but the CCDF, complementary cumulative distribution function of the exponential distribution evaluated at s plus t. That is simply given by e power of minus lambda into t plus s. On the denominator you will have e power of CCDF evaluated at s, e power of minus lambda s. So you can split it into two exponential, e power of minus lambda t into e power of minus lambda s, and the lambda t gets cancelled factors. You will have e power of minus lambda s, which is again a CCDF of an exponentially distributed random variable with a parameter lambda. Therefore, if you view x, we find that x to be an exponential distribution with the same parameter lambda. See, we have shown that if x is exponentially distributed, then its density function will be given by lambda e power of minus lambda x for x greater than 0 and so on. And the CDF is 1 minus e power of minus lambda x and all those things. We can also show that if the CDF takes the form 1 minus e power of minus lambda s, then it has to be an exponentially distributed random variable with parameter lambda. That is what we are invoking here. So we see that the process forgets the time it has been that has passed, and it still behaves like as if it is a original process. So the waiting time yes is not going to influence the remaining time t that you have to wait. So we call this as the memoryless property of the exponential distribution. Note that in the case of continuous valued random variable, it is only the exponential random variable which has this memoryless property. No other continuous valued random variable has this memoryless property. We can go one step ahead. If you consider a random variable and force it to have a memoryless property, that is this equal to this, that is probability that x greater than s plus t given x greater than s is equal to probability x greater than t. That is what we call as the memoryless property. For some random variable x, then x has to be exponentially distributed. Okay, so it's a necessary and sufficient condition. And coming to the discrete valued random variable, geometric random variable is the only discrete random variable which has the memoryless property. So these two are very closely tied up with the DTMC and CTMC respectively. That is why we pay so much attention towards this distribution. Then we will look at one very important property which is quite useful in the theory of reliability. So often we model the lifetime of a component, of a person, and so on, as using reliability theory, how reliable the process is or a product it, and so on. So to this end, we develop some formalism, some simple functions, and again the exponential distribution makes the analysis simple and also acts as a good model for certain under certain conditions. First, we will define what is called as the failure rate, also called as the hazard rate. What we mean by that is, if you have a continuous positive valued random variable x, which has a distribution f, capital F, and of course the density function small f, his failure rate or hazard rate, we will denote it as R of t, is defined as the instantaneous failure rate of the random variable, given that it has survived till a given time t. That is, if you interpret it as a component lifetime, if you assume that x to be a random variable that signifies the lifetime of a component, given that the component has not failed till a given time t, what is the density function governing its lifetime just after t? That is what we mean by the failure rate or hazard rate. That is, if this signifies the density function of the failure of the component, of the lifetime of the component just after the time t, given that it has survived till time t, then probability that x lies between t and t plus delta t is given by R of t into dt, and that can be shown to be like this. Now, you know that f of t is the density function of x, which is an unconditional one, without having any knowledge about the survival of the component. Okay, that to begin with, when we start using the component, f of t is the density function. But suppose you are told that the component has survived till a time t, then given this condition, you have to normalize the density function by the factor that this component has survived. The probability that the component has survived is, the component will survive till time t, is probability that x is greater than t, which is given by the CCDF of the x evaluated at t, which is 1 minus fx of t. So you have to divide this density function by this probability to get the density function at time t given that x is greater than t, and that is what precisely we mean by the failure rate or hazard rate. Okay, whatever I mentioned can be formally stated as follows. That is, what is the probability that x is an element of t and t plus delta dt given that x is greater than t? Given that the component has survived till t, it means that x has to be greater than t. What is the probability that it will die or it will fail in this small interval t and t plus dt? And this is what we are trying to find out. If we interpret it as a density function, then that function into dt will be this probability. You just want to extract that function. It will be multiplied by dt, of course. So again, this is looks like probability of a given b. It can be written as a intersection b by b. So it is x element of t and t plus dt comma x greater than t divided by this. You will see that if x lies between this interval, obviously it has to be greater than t. So this condition is not required. So this is what we have to look at. And what is this? This is nothing but probability that x lies between t and t plus dt. It is nothing but the product of the density function evaluated at t multiplied by the interval size dt. So it is small fx of t into dt. And the denominator, you have the CEDF, which is 1 minus fx of t. So if you look at this one, if you take this part, then this looks like a density function because you are multiplying it by dt. Okay, so this is called as the failure rate or a hazard rate or instantaneous failure rate given that the component has survived till time t. So we will denote it as R of t. So the R of t represents the conditional probability density function that a t-year-old item will fail. Well, now suppose you have a function item that doesn't age. That is, age will not influence the working of the item. That is, okay, whatever may be the age of the item, its failure rate is independent of the time it has been surviving. Then obviously this will be the memoryless property of the it will denote the memoryless property of the distribution. So in that case, R of t should be independent of t because the instantaneous failure rate of a t-year-old item is not dependent upon t. It is new as if it is a freshly taken item component irrespective of its age. So R of t has to be independent of t, so it has to be a constant. We will see that this is what precisely happens for an exponentially distributed random variable. For x, which is expo with parameter lambda, what is R of t? R of t is f of t by definition by 1 minus fx of t. So you substitute lambda e power of minus lambda t on the denominator e power of minus lambda t, that is equal to lambda. You will see that the hazard rate is constant, which is lambda. So that shows that it has memoryless. Okay. It can also be shown that if we have a random variable with distribution whose failure rate is constant and independent of the time, then it has to be an exponentially distributed random variable. Okay. That can also be shown. That is, if R of t is a constant, then you can see that this is nothing but the numerator you can write it as d by dt of capital F of t divided by 1 minus f of t. You can write it as log of 1 minus fx of t, okay, and so on, with and equal to minus that constant lambda, and then integrate on both sides, and then you will get 1 minus fx of t is equal to e power of minus lambda t, and so on. You will get that distribution of exponential distribution, you will get it back. So this is very important property. Then we will see that suppose x1, x2, xn are all independent exponential random variable. Okay, xi is exponential with a parameter lambda i varying from 1 to n. Suppose you put into use all these components at the same time, and you are looking at the time at which the earliest failure of a component out of the n components that is under service. Obviously this is nothing but the minimum of x1, x2 to xn. So xi indicates the lifetime of the ith component. So the minimum of the one is the time at which the first failure occurs. So this will be useful in modeling reliability, because if you have a system in which there are n components, and if the system will fail, even if one of the component fails, then the lifetime of the overall system is equal to the minimum of the lifetime of all its component. So that is where this problem will find useful. So minimum of x1 to xn is what we are interested in. That itself is a random variable. We will call it as x. And how will that be distributed? To do that, we will look at the CCDF of that random variable x, which is the minimum of x1 to xn. So what is the CCDF? Probability that x is greater than x, small x. That is probability that minimum of x1 to xn is greater than small x. This is the CCDF. So this can be written in the following manner. If the minimum of x1 to xn has to be greater than x, obviously each and every one of these x1, x2 to xn has to be greater than x. Then only the minimum itself will be greater than x. So this condition is the same as the condition probability that xi is greater than x for all I is equal to 1 to n. So each and every one of these conditions has to be equal to 1. So it is an intersection of all these events. Xi is greater than x, intersection x1 is greater than x, intersection x2 is greater than x, and so on. And x1, x2 are all independent exponential random variable. That is, the failure of one component will not affect the other component. Because they are all independent, and these events are all independent events, that is x1 greater than x is independent of x2 greater than x, and so on. So the probability of the intersection of all these things is the product of the probabilities. Therefore we write pi I varying from 1 to n probability that xi is greater than x. And this is nothing but the CCDF of xi, which is e power of minus lambda I into x. So you will have pi I varying from 1 to n e power of minus lambda I x. So this product of exponential means it is the exponential of the sum. Okay. So you can take this pi into the exponent and convert it into n sigma. So it is e power of minus sigma I varying from 1 to n lambda I into x. So we find that this minimum of x1 to xn, which is the random variable x, greater than being x, is the CCDF of the random variable minimum that has this form. And this form means that it is exponentially distributed. What is its parameter? Parameter is sigma I varying from 1 to n lambda I. So we find that the minimum of x1 to xn is also exponential in nature, and its parameter is the sum of the parameters of the comprising exponential random variables. And so the parameter is sigma I varying from 1 to n lambda I, and therefore the mean or the expectation of the minimum, that is E of x, has to be 1 over sigma I varying from 1 to n lambda I. So this is a very important conclusion we arrive at. So we have got the expected lifetime of the system in terms of the expected lifetime of the components. We can tell that this is said to be, components are said to be in series, because even if one component fails, the system fails. It is not to be understood that the series connection is motivated by the way the electrical components are connected in an electrical circuits, but in a mechanical component, we use the term series. We have to only interpret that the system fails even if one of the component fails. That is what we mean. Now we will look at one more important property of the exponential distribution. Suppose we have got two exponentially distributed random variable x1 and x2 with the respective parameter lambda 1 and lambda 2. Therefore their mean or expectation will be 1 over lambda 1 and 1 over lambda 2. We would like to know what is the probability that x1 will be less than x2. That is, x1 will fail before x2. Okay. We will use this to model some cases like, suppose two customers are getting service from two servers parallelly, and the service time is exponentially distributed with parameter lambda 1 and lambda 2. We are asking what is the probability that the customer 1 will complete the service before customer 2. For such questions, this problem will be used for modeling. So the question is probability that x1 is less than x2. That we can find out the following. Let us condition this by the value of x1 and then uncondition is. Given that x1 is equal to small x, then this probability is probability that x1 is less than x2 given x1 equal to x. That is what we have to find. And we have to uncondition by multiplying it by the probability that x1 is equal to x, and then integrate it over the entire domain of x. That is, we have to multiply it by the density function of x1 evaluated by x and integrate it over the whole range. So it is integral 0 to infinity this case into lambda 1 e power minus lambda 1x dx. Now this one, given that x1 is equal to x, we can put x in this place. That is probability that x is less than x2 or x2 is greater than x. X less than x2 or x2 greater than x, which is nothing but the CCDF of x2, which is e power of minus lambda 2x. So we have to do an integration 0 to infinity e power of minus lambda 2x times lambda 1 e power of minus lambda x dx. We will take the lambda 1 outside and then club these two exponents. It is e power of minus of lambda 1 plus lambda 2 into x dx. You will see that this gives 1 over lambda 1 plus lambda 2. Therefore, we will see that this is nothing but lambda 1 by lambda 1 plus lambda 2. So, if lambda 1 is smaller than lambda 2, then you will see that this probability is less than 0.5. Okay, because the probability will be less. Lambda 1 will, if lambda 1 is less than lambda 2, 1 over lambda 1 is greater than lambda 2, So the component 1 is supposed to survive more than the component 2, and therefore this probability will be less than 0.5. That is what we meant. The question probability that x2 greater than x1, similarly you can derive, and it has to be lambda 2 by lambda 1 plus lambda 2, which is also obvious because there is only two ways in which it can happen. x1 has to be less than x2, or x2 has to be less than x1. x1 equal to x2 has zero probability. So you can simply obtain that probability by subtracting this from 1. You can also solve this in an intuitive manner, that probability that x1 less than x2 is the expected value of x2 divided by the sum of the expected value of x1 and x2. Okay, so here we put the expected value of x2, that is to be noted. Sorry, expected value of x1. So you would see that this is nothing but 1 over lambda 1 by 1 over lambda 1 plus 1 over lambda 2. Sorry, this has to be expected value of x2, then you will get this one. So this is another way in which you can get it. So we have looked at some of the interesting properties of exponentially distributed random variable. We will stop at this point. We will look at some more properties of 2 or more exponentially distributed random variables. We will look at gamma distribution, hypo exponentially distributed random variable, hyper exponential random variables, and so on in the next lecture. Thank you.